Welcome back to the deep dive. Today we're looking at something really fundamental, the hydrogen atom.
The simplest one out there, right? Just a proton and an electron.
Exactly, it should be simple. But, well, figuring out its energy levels precisely, that didn't just confirm quantum theory, it actually broke one of the most celebrated equations in physics.
Oh, absolutely. It's a classic case of measurement pushing theory to its limits and then beyond.
So let's set the scene a bit. The history goes back quite a way.
It does. You had Balmer back in 1885 sorting out the spectral lines, and then not long after, Michelson and Morley noticed those lines weren't single, they were split, doublets.
That was the first real clue about this fine structure thing.
Right. Then, of course, you needed quantum mechanics to explain the lines at all. That was Bohr, 1913.
And Sommerfeld tried to explain the splitting, the fine structure, in 1916 using early relativistic ideas.
Yeah, adding corrections. But the real heavyweight theory, the one that looked like it had solved everything perfectly, came from Paul Dirac in 1928.
Dirac. His equation for the electron was just elegant. A masterpiece.
It really was. It naturally gave you the electron's wave nature, its charge, and crucially, its spin, that intrinsic angular momentum.
When the magnetic moment associated with that spin too, right?
Exactly. All falling out of the math, not just tacked on. It was beautiful.
So when he took this amazing equation and applied it to hydrogen, it predicted the fine structure, the energy level splitting with incredible accuracy.
It did. But here's the crux, and this is our mission for this deep dive. That perfect prediction had a flaw, a tiny one, but critical.
We need to unpack why it failed, how experimenters proved it failed, and then the radical new physics needed to explain reality. That's quantum electrodynamics, QED.
Okay, so let's zoom in on the second energy level, N2. Dirac's theory made a very specific claim about two states within that level.
The 22s12 and the 22p12 states.
Those are the ones. His theory said they should have precisely the same energy. Perfectly degenerate, we'd say.
Okay. Quick recap for you listening. S and P tell you about the electron's orbital motion. S means zero orbital angular momentum.
Right, that's the state where the electron, classically speaking, dives closest to the nucleus.
And P has 1 unit of angular momentum, so it orbits a bit further out, on average.
Yeah. And Dirac saying they had the same energy, that came directly from assuming the simplest possible interaction. Just the basic inverse square Coulomb attraction.
Like planets orbiting the sun, but with electric charges?
Sort of, yeah. If experiments found any energy difference between that S and P state, even a tiny bit, it meant the force law wasn't that simple. Something else was going on.
So, okay, why was testing this specific prediction so important? Dirac's equation was working so well elsewhere. Why hunt for a difference that the math said should be zero?
Well, context matters. By the 1930s, particle physics was exploding. Kind of chaotic, actually.
Right, you had the neutron discovery, the neutrino was proposed, then mesons, hyperons, a whole zoo.
Exactly, a deluge, as Lamb called it. So, it's discovering all these new particles. There was this growing need to really nail down the properties of the ones we thought we understood best, the electron and the proton.
Like a quality control check on the fundamentals before building more complex theories on top.
Precisely.
Yeah.
Could we trust our model of the electron if we hadn't pushed the tests to the absolute limit in the simplest atom possible?
And the initial tests using spectroscopy, they weren't quite sharp enough.
They weren't definitive. Some early work, like from Houston and Williams, actually did hint there might be a separation, but the results were kind of ignored or dismissed. The expected effect, if any, was just too small for optical methods at the time.
So it needed a completely new approach, something with much higher precision.
Which brings us to the post-war era, the mid-1940s, and crucially, the expertise gained from wartime radar development, microwaves.
Enter Willis, Lamb, and Robert Retherford.
Yes, they tackled the experimental challenge head-on, and it was a challenge.
What were the main hurdles?
Two big ones. First, if you just use a standard hydrogen gas discharge lamp, the atoms are getting knocked around violently. It broadens the energy levels, smearing out any tiny splits.
Okay, so you need a gentler way to handle the atoms.
Right. Second problem. In that discharge, you tend to populate all the excited states, like the S and P states we care about, pretty much equally.
And if you have equal numbers in both states, shining radio waves on them doesn't do much.
Exactly. You need a population difference to see net absorption or emission. If they're balanced, you get stimulated emission canceling out absorption. Nothing changes overall.
So Lamb needed a trick. A way to get a bunch of atoms only in the S state, or mostly in the S state, and then see if you could nudge them over to the P state with microwaves.
And the trick was brilliant.
Yeah.
Use metastable atoms.
Metastable.
It means the state is unusually long-lived, specifically the 22s12 state.
Why is it long-lived?
Well, think classically for a second. An S state is spherically symmetric. A perfectly round ball of charge doesn't radiate electromagnetic waves easily. Quantum mechanically, the selection rules forbid a direct, simple decay to the ground state by emitting just one photon.
So it just sits there in that excited state for ages.
Relatively speaking, yes. Its lifetime is maybe a fraction of a second, which is an eternity compared to the 22p12 state.
How long does the P state live?
About a billionth of a second, poof, it's gone back to the ground state.
Okay, so the S state is stable enough to work with. That's the key.
That's the lever. So they built this apparatus. First, they break up hydrogen molecules, H2, into individual hydrogen atoms, H.
Okay.
Then they use an electron beam, carefully controlled, to bump some of those atoms into the excited states. But it's inefficient. Only a tiny fraction, maybe 1 in 100 million, ends up in the desired metastable 22s12 state.
1 in 100 million. Wow. But you get a beam of just those atoms.
Well, a beam containing some of those metastable atoms, along with lots of ground state atoms. But the key is you have some metastable ones.
And you direct this beam towards a detector. How did they detect just the metastable ones?
Cleverly simple. The detector was just a piece of metal. The metastable 22-style atoms carry a lot of internal energy. When they hit the metal surface,
They release that energy.
yes, and they knock electrons out of the metal surface. Those ejected electrons create a tiny electric current.
An electrometer current. So current equals metastable atoms hitting the target.
Exactly. That's your baseline signal. More metastable atoms arrive, you get more current.
Okay, baseline established. Now how do you measure the S to P energy gap?
You pass the beam of atoms through a region where you apply a radio frequency field, microwaves, actually.
Microwaves.
Right.
Like from the radar tech.
Precisely. And often they'd also apply a magnetic field. That helps to split the levels a bit further, making things easier to resolve. But the core idea is the microwave field.
And you tune the frequency of those microwaves.
You sweep the frequency. If the microwave frequency hits exactly the right value, the energy difference between the $22 state and the 22 PCR state, then something happens.
The microwave photon gets absorbed.
Yes, it kicks the atom from the long-lived $22 state up to the short-lived 22 PCR state.
And that P state decays almost instantly.
In about a nanosecond, yes. It falls down to the ground state, spitting out an ultraviolet photon.
So the atom that was metastable is now in the ground state.
Correct. It's been quenched, we say,
Yeah.
and a ground state atom hitting the detector.
Doesn't have enough energy to knock out an electron.
Exactly. So when the microwaves are tuned to the right frequency, suddenly fewer metastable atoms reach the detector.
The electrometer current drops.
Bingo. You see a dip in the current at that specific frequency, a resonance. You're detecting the disappearance of the signal, not the absorption itself. It's incredibly clever.
That really is brilliant. So you find the frequency that causes the biggest dip, and that frequency tells you the energy separation.
That's the measurement. And the result, published by Dayhoff, Triebwasser, and Lamb in 1947, using deuterium first, actually, was unambiguous.
Not zero separation.
Definitely not zero.
Yeah.
They measured a shift, a separation between the 22s12 and 22p12 levels of 159 megacycles per second. Megahertz, we'd say now.
159 megahertz. And the uncertainty.
Remarkably small for the time. About 0.1 megahertz, 0.1 mcsec.
So Dirac's beautiful, perfect equation, the bedrock of relativistic quantum theory, was wrong. Or at least incomplete.
Fundamentally incomplete. That tiny shift, roughly 1 part in 1,000 of the total fine structure splitting, it caused an earthquake in theoretical physics.
It demanded a whole new way of thinking,
Yeah.
which brings us to QED, quantum electrodynamics, and the initial mess it created.
Right. The experiment basically screamed. The electron isn't just a simple point charge interacting via a simple Coulomb force.
Yeah.
But the problem was, how do you describe it otherwise?
People tried thinking of the electron as a tiny sphere, right? But that caused problems.
Huge problems. Trying to make an electron have a finite size immediately clashed with Einstein's theory of relativity. It got very ugly very quickly. Dirac's point-particle approach was the only one consistent with relativity.
So they had to stick with the point electron, but somehow modify how it interacts.
Yes. The next logical step was to combine Dirac's equation for the electron with the quantum theory of the electromagnetic field itself. That's QED.
Quantizing the field, meaning treating light and electromagnetism as particles, as photons.
Essentially, yes. And allowing the electron to interact with these quantum fluctuations of the field. But when they try to calculate that interaction,
Disaster struck.
Pretty much. When theorists calculated the effect of the electron interacting with its own electromagnetic field, its self-energy, you could call it,
They got infinity.
total, complete, utter infinity. For the electron's energy, for the shift in the spectral lines, meaningless results,
Not just a big number, but mathematically infinite.
infinite. It was a return of the old ultraviolet catastrophe from classical physics, but now inside quantum theory itself.
Where was this infinity coming from? What was the physical idea behind it?
It came from the quantum vacuum. The idea in QED is that empty space isn't truly empty. It's constantly fizzing with virtual particles. Virtual photons, in this case, popping into and out of existence.
The zero-point energy of the field.
Exactly, zero-point fluctuations. The electron is sitting there, bathed in this sea of virtual photons of all possible energies, all frequencies, and it interacts with them.
Okay.
The problem arises when you consider the interactions with very high energy, high frequency virtual photons. There are infinitely many possible frequencies, stretching up to infinity. When you sum up all those tiny interactions,
The sum blows up.
it diverges.
It diverges. So the theory, as it stood in the 1930s, predicted that the electron's interaction with the vacuum gave it infinite energy and would shift every spectral line by an infinite amount.
Which is clearly nonsense. Atoms exist, spectral lines are sharp. The theory was fundamentally broken.
It looked like a dead end. Oppenheimer had pointed this out way back in 1930. It was a major crisis. So how did they fix it? This feels like the point where you need some kind of mathematical wizardry. Or maybe cheating.
Well, the fix did feel like cheating to many physicists at the time, even the ones who developed it. It's called renormalization.
Renormalization. Okay. It sounds like just redefining things until the infinities go away.
That's not entirely unfair, actually. But there was a crucial physical insight. The story goes that Hans Bethe had the key idea on a train ride back from the Shelter Island Conference in 1947, right after hearing about Lamb's result.
The famous train calculation, he did it on the back of an envelope or something?
Something like that. Bethe realized something critical. This infinite energy they were calculating for an electron bound inside a hydrogen atom. It looks suspiciously like the infinite energy the theory also predicted for a completely free electron, just sitting alone in space.
Okay. So both are infinite. How does that help?
Because we can never measure the total energy of a free electron, including its infinite self-energy. What we measure in the lab is the final physical mass of the electron. That measured mass does already include all these infinite self-interaction effects.
So the infinity is sort of absorbed into the definition of the physical electron we start with.
That's the core idea of renormalization, you say. Look, the bare electron in my equations has some infinite mass and infinite self-energy. But the physical electron, the one I actually observe, has the measured mass m. This m is the bare mass plus the infinite self-energy correction. We renormalize the mass.
So you subtract infinities.
You subtract the infinite self-energy calculated for a free electron from the infinite self-energy calculated for the bound electron in the hydrogen atom. The infinities are presumed to be the same, representing the electron's fundamental interaction with the vacuum.
And when you subtract one infinity from the other...
You hope you're left with something finite. And B showed in his rough calculation that you were. You were left with a small, finite energy difference.
Yeah.
A shift.
The difference in the self-interaction effects caused by the electron being near a proton compared to being free.
Precisely. That difference is calculable. It's
Yeah.
finite. And it should be observable.
And did Beth's number match Lamb's experiment?
His first non-relativistic calculation gave something remarkably close, around 1,000 MSec. It was immediately clear this was the right path.
Okay, the math works, maybe, but it still feels a bit abstract. Is there a more physical picture of what's happening?
Yes, absolutely. T.A. Welton provided a really helpful picture in 1948. Think about those zero-point fluctuations, that sea of virtual photons in the vacuum.
Okay, the fizzing empty space.
That fluctuating electromagnetic field constantly pushes and pulls on the electron. Makes the electron jitter randomly around its average position.
So it's not sitting still, it's vibrating really fast.
Exactly. It's executing this rapid, tiny, random motion. The point electron effectively gets smeared out into a fuzzy little ball, maybe around 10, 12 centimeters across.
So it's not a perfect point anymore because the vacuum is shaking it?
That's the picture. Now, think about the hydrogen atom again. An electron that's a fuzzy ball instead of a sharp point. How does it interact with the proton?
If it's spread out, maybe the attraction isn't quite as strong when it gets really close to the proton?
Exactly. A point electron feels the full, intense pull of the proton's charge when it's right on top of it. But a fuzzy electron averaged over its little cloud, feels a slightly weaker attraction at very short distances.
Okay, I see. The smearing smooths out the force a bit.
Right. Now remember the S&P states.
The S state spends more time near the proton. The P state stays further out.
So which state will be more affected by this weakening of the force at short distances?
The S state, because it's the one diving close to the proton where the force is being slightly reduced by the smearing.
Precisely. The S-state electron cloud feels less attraction than Dirac's point electron would have. Less attraction means it's less tightly bound.
Less tightly bound means higher energy.
Yes. The 22s12 state gets pushed up in energy relative to the 22p12 state, which spends less time near the nucleus and is less affected.
And that upward push is the Lamb shift.
That upward push is the Lamb shift. It's the energy cost of the electron jittering in the vacuum fluctuations experienced most strongly by the state closest to the nucleus. It's around 1,000 MsEK from this effect.
That's incredible. The vacuum itself is tweaking the energy levels of the atom.
It is, and this jittering calculation wasn't the whole story. QED predicted other smaller vacuum effects too.
Like what?
There's something called vacuum polarization. The vacuum can momentarily create virtual electron-positron pairs. These pairs slightly screen the proton's charge, changing the force law. That contributes about 27 MsEK to the shift.
Of another vacuum effect.
And there's also the fact that the electron's magnetic moment isn't exactly what Dirac predicted. There are QED corrections to that too, the anomalous magnetic moment. That affects how the electron's spin interacts with its own motion, adding another 68 MsEK or so.
So you add up the jittering effect, the vacuum polarization, the magnetic moment correction.
And when the dust settled, and the much more rigorous relativistic QED calculations were done by people like Feynman, Schwinger, Tominaga, and Dyson, the theoretical prediction landed right on top of Lamb's measurement.
What was the agreement like by, say, the mid-1950s?
By 1955, when Lamb gave his Nobel Lecture, the theory and experiment agreed to within about 0.5 MsEK. Stunning agreement.
So this tiny measurement, 1 part in a million of the atom's total energy, really validated this whole wild picture of QED and renormalization.
Absolutely. It was the crucial test. It showed that QED, despite the weirdness of infinities and renormalization, was the correct description of electromagnetism at the quantum level.
So wrapping this up, why should you, our listener, really care about this sp split in hydrogen? What's the big takeaway?
Well, first, it was arguably the most precise verification of a fundamental force law ever achieved at that time. Getting agreement to 0.1 MsEK meant confirming QED to a few parts per billion. That's extraordinary.
It proved the theorists were on the right track, even with the seemingly crazy math.
Yes. And second, it has a lasting legacy in fundamental constants. Measuring that fine structure splitting accurately gives us our best handle on a really important number.
Alpha, the fine structure constant.
Exactly. That dimensionless number, roughly 1137, that governs the strength of all electromagnetic interactions. The Lamb shift measurement pins down alpha more directly and accurately than almost any other method.
So a precise measurement inside the simplest atom tells us about a universal constant governing light and matter everywhere.
That's the power of it. But maybe the most profound takeaway, the real mind-bender,
Go on.
is what it taught us about empty space. The Lamb shift, confirmed in 1947, was the first definitive experimental proof that the vacuum is not empty.
It's not just nothingness.
It's a dynamic, fluctuating, energetic medium, a sea of virtual particles that constantly interact with real particles, subtly changing their properties, shifting their energies.
That tiny energy gap Lamb measured is direct evidence of the hidden turbulence of the quantum vacuum.
Precisely. It showed us that even the simplest atom is constantly being dressed and influenced by the complex reality of seemingly empty space. A truly revolutionary insight, all thanks to a careful microwave experiment.